Happy morning, students. Today we are going to see chapter 10, circles. The collection of all the points in a plane which are at a fixed distance from a fixed point in the plane is called a circle. This fixed point is called as the center of the circle, and the fixed distance from the center is called as the radius of the circle. So in the adjoining figure, O is the center and OP is called as the radius of the circle. The circle divides the plane into three parts. First one, interior region of the circle. Second, exterior region of the circle. Third one, on the circle. Terms related to a circle. Radius, a line segment joining the center and a point on the circle is called its radius. So the plural of radius is radii. The given figure OA and OB are called as the radii of the circle with center O and radius R. Circumference. The perimeter of a circle is called as the circumference of the circle, where you have the formula circumference of a circle is 2 pi r. Chord. A chord of a circle is a line segment joining any 2 points on the circle. So he has given that PQ and AB are the 2 chords of a circle with center O, where the chord passing through the center O is called as a diameter. Diameter. A diameter is a chord of a circle passing through the center of the circle. So in the adjoining figure, AB is called as a diameter with center O. A diameter is the longest chord of a circle. So diameter is equal to 2 times of radius. Secant. A line which intersects a circle in 2 distinct points is called as a secant of the circle. In the given figure, the line L passing inside the circle, touching the circle at 2 points A and B. So L is called as a secant of the circle. Segment of a circle. The part of the circular region which is bounded by an arc and a chord, including the arc and the chord, is called a segment of a circle. The segment containing the minor arc is called minor segment, and the segment containing a major arc is called major segment. Thus, APQA is called minor segment of the circle. So, the minor and the major segment of a circle are called the alternate segments of a circle. Sector of a circle. The region enclosed by an arc of a circle and its 2 bounding radii is called a sector of the circle. In the given figure, the region which is occupied between the 2 radii with an arc of a circle is called sector. There are 2 alternate sector. One is a minor sector, other is a major sector. Minor sector is the region occupied between the 2 radii with the smaller arc of the circle. The major sector is a region occupied between the 2 radii with the bigger arc of the circle. Theorem 10.1. Equal chords of a circle subtends equal angles at the center. So he has given a circle with center O and 2 chords AB and CD. We want to find out that angle AOB is equal to angle COD. So given a circle with center O and radius R in which the chord AB is equal to the length of the chord CD, we want to prove the angle subtended by the chord were equal, that is angle AOB is equal to angle COD. Let us consider triangle AOB and triangle COD. We have OA is equal to OC, radii of the circle. OB is equal to OD, radii of the circle. It is given in the statement AB is equal to CD. So I got 3 sides of triangle AOB and triangle COD are equal. So by SSS congruence criteria, triangle AOB is congruent to triangle COD. Hence by CPCT, I can say that angle AOB is equal to angle COD. Hence I proved that equal chords of a circle subtends equal angles at the center. Theorem 10.2. If the angle subtended by the chords of the circle at the center are equal, the chords are equal in their length. Given a circle with center O and radius R in which the chords AB and CD subtends an angle at the center, and it is given that those angles are equal to each other. To prove AB is equal to CD, that is the chords were equal. Consider triangle AOB and triangle COD. We have OA is equal to OC, radii of the circle, OB is equal to OD, radii of the circle, and it is given angle AOB is equal to angle COD. We got two sides and one angle which is included between these two sides are equal. So by SAS congruence, triangle AOB is congruent to triangle COD. Hence I can relate that AB is equal to CD by CPCT. Theorem 10.3. The perpendicular drawn from the center of a circle to a chord bisects a chord. So he has given the circle with center O and he has given the perpendicular line OL, where the perpendicular line is drawn from the center and a chord AB touching the chord at the point L. We need to prove that OL bisects AB. Coming to the solution, given a chord AB of a circle with center O and radius R and OL is perpendicular to AB, to prove LA is equal to LB, construction, join OA and OB. Let us consider right triangle OLA and triangle OLB. We have OA is equal to OB, radii of the circle, and the second point I got OL is a common to both the triangles. We know that OL is perpendicular to AB, so OLA is equal to OLB, which is equal to 90 degree. So by RHS criteria of congruence, we find that one side and one hypotenuse of the triangle OLA and OLB are equal to each other. So we get triangle OLA is congruent to OLB. I can relate my LA and LB are equal by CPCT. Theorem 10.4. The line drawn through the center of the circle bisects a chord is perpendicular to the chord. He has given a circle with center O and he has given that AB as a chord, where OM line drawn to a chord AB. We need to prove that OM is perpendicular to AB, which means that OM subtends an angle 90 degree with the base AB. Even M is a midpoint of chord AB of a circle with center O and radius R, we need to prove OM is perpendicular to AB. Construction, join OA and OB. Let us consider triangle OMA and triangle OMB. We have OA is equal to OB, radii of the circle, and OM is common to both the triangles, and MA is equal to MB, as we have seen that the line OM bisects the chord AB. So by SSS congruent, triangle OMA is congruent to triangle OMB. That angle OMA is equal to angle OMB laid by CPCT. We know that OM is a line, stands on a straight line. I can relate this angle OMA and OMB by the linear pair axiom. We get OMA plus OMB is equal to 180. But we know that angle OMA is equal to OMB. So in place of OMB, I am substituting OMA. So I get 2 times of OMA is equal to 180. Hence I get OMA is equal to 90. And similarly, my OMB will also be equivalent to 90. Hence OM line is perpendicular to AB. Exercise 10.1. First one, fill in the blanks. The center of the circle lies in dash of the circle. So he has given an option exterior and interior. So since the center of the circle lies inside the circle, so I am writing interior. Second one, a point whose distance from the center of the circle is greater than its radius lies at its exterior of the circle. The longest chord of a circle is called diameter of the circle. Fourth one, an arc is a semicircle where its ends are the ends of the diameter. Fifth one, segment of a circle is a region bounded between an arc and a chord of a circle. Sixth one, a circle divides a plane on which it lies in 3 parts, that is interior, exterior, on the circle. Second question, write true or false. Give reason for your answer. First one, line segment joining the center to any point on the circle is called the radius of the circle. The line segment joining the center to any point on its circumference is called radius. So the first one is True. Second one, a circle has only finite number of equal chords. False, because we have studied that a circle has an infinite number of equal chords can be drawn. Third one, if a circle is divided into three equal arcs, each is a major arc. We know that a major arc will be more than a semicircular arc length. So if a circle is divided into three equal arcs, it cannot be more than semicircular arc. So each circle, if it is divided into three equal arcs, it must be a minor arc. It's not a major arc. So the statement is false. Fourth one, a chord of a circle which is twice as long as its radius is the diameter of the circle is true. Fifth one, sector is a region between the chord and its corresponding arc. Since we studied that segment is a region bounded between the chord and the corresponding arc, so the statement is false. Sixth one, a circle is a plane figure. It's true. Exercise 10.2, first problem. Prove that equal chords of congruent circles subtends equal angles at the center. Given two congruent circles with the equal chords AB and CD, we want to prove that the angles subtended by the two chords are equal. Given two congruent circles with center O and O dash with the same radius R, which have chords AB and CD respectively, such that the two chords are equal. To prove angle AOB is equal to angle CO dash D, let us consider triangle AOB and triangle CO dash D. We have AB is equal to CD, it is given chords were equal, and OA is equal to OC dash equal radii. Similarly, OB is equal to OD dash equal radii. By SSS criteria of congruence, triangle AOB is congruent to triangle CO-D. Hence, I can relate that angle AOB is equal to angle CO-D by the CPCT, that is corresponding parts of the congruent triangles. Second problem, prove that if the chords of the congruent circles subtends equal angles at their center, then the chords are equal in their length. Given two congruent circles and the chord AB and CD where it subtends an angle AOB and COD, he has given that angle AOB is equal to, coming to the solution, given two congruent circles with center O dash and same radius R which have the chords AB and CD respectively, such that angle AOB is equal to CO dash D. To prove the chords were equal in their length, that is AB is equal to CD. Consider triangle AOB and triangle CO dash D. We have OA is equal to O dash C, radii of the circle. Similarly, we have OB is equal to O dash D, radii of the circle. It is given that angle AOB is equal to angle CO dash D. It is given in the statement. By SAS congruence criteria, triangle AOB is congruent to triangle CO dash D. Hence, I can relate that AB is equal to CD by CPCT, that is corresponding parts of congruent triangles.